Hello friends. So today we are going to solve few questions, rather we can say three questions, and these three questions are from collision, which consists of conservation of momentum as well as energy. Okay. So the first question, it states that a particle of mass capital M undergoes an elastic collision with a second particle of mass small m that is initially at rest in the laboratory frame. If capital M is less than m, the incident particle can rebound and move directly backward after the collision. If m is greater than small m, the incident particle cannot reverse its directions. Instead, there exists a maximum possible deflection angle for its trajectory. Show that for the case m is greater than m, the maximum scattering angle theta max of the incident particle in the laboratory frame is given by sine inverse m upon m. So basically, in this case, we are going to find out what will be the maximum deflection angle for the mass capital M after the collision. So in this case, we are going to use both the conservation of our momentum as well as energy. Okay, and we can just draw an approximate figure, and we are given that we are having a mass capital M, and suppose it is moving towards right side with the velocity v, and we have another mass small m which is at rest, and they are going to collide with each other such that we can say that our capital M is having a velocity after the collision. Let us call this as v prime, and angle with respect to the initial direction of motion is our phi. And for the small m, let us suppose it is moving in the opposite direction, and its velocity is our small v prime, and its angle with respect to the horizontal is our gamma. And we can divide the respective velocities into the components, and so the component of our this m, or we can say our v prime, we can write this as v prime cos of phi, and its horizontal component will be v prime sine of phi. Similarly, for the other one, we are going to get this as v prime cos of gamma, and we are going to get this as v prime sine of gamma. This is the basic, their velocity and their components. Okay. And initially, only the mass capital M is moving with the velocity v. The small m is at rest. Okay. So we can use the conservation of momentum respectively x-axis as well as with respect to y-axis. So you can say that conservation of momentum, we can say momentum conservation and let us take first of all our x-axis. and we can say that as a p of x, and for that the initial momentum will be equal to over only mass capital M is moving, so this comes m times v will be equal to, we have this as m v prime cos of phi plus small m small velocity prime and cos of gamma. And let us call this equation number 1. Similarly, we can write the momentum conservation along our y-axis. Okay, so everything for initial momentum is along our x-axis. So therefore, along y-axis that will be equal to 0, and we are going to get this as m v prime sine of phi minus m v prime sine of gamma. This is our equation number 2. And the collision is elastic, therefore we can also use our energy conservation. You can say our energy conservation, and this energy conservation will be giving us half m v square is equal to half m v prime square plus half m v prime square, and this half is going to cancel out throughout, and this will give us that our mv square is equal to m v prime square plus m v prime square. And we have two equations, equation number 1 and equation number 2. So let us call this as equation number 3. So we are going to use equation number 1 and 2 and manipulate it, make some left-right adjustment. So we can say equation number 1, we can write this as our mv prime cos of gamma is equal to over mv minus mv prime cos of phi. And from equation 2, we can write this as our mv prime sine of gamma is equal to mv prime sine of phi. Let us call the equation number 4 and this is equation number 5. So we are going to square equation number 4 and 5 individually and add them. Okay. So you can say equation number 4 its square plus equation number 5 and its square. And on our left side, we are going to get cos square plus sine square, that will be equal to 1. Therefore, we can say on the left side we get this as our m square and v prime square is equal to, on the right side we are going to get first term will be our m square v square plus m square v square, and we have this as cos of phi minus, and this will be over twice m square v prime cos of phi. Okay. And this is our first equation, and then we are going to add them in the square of the second equation, and second equation is our m square v prime square, and we have this as sine square phi. Okay. And so in this we can clearly see that these two terms, okay, here I forgot to mention this will be square. Okay, so we are going to get cos square phi as well as sine square phi, that will be equal to 1. Okay. And we can take m square common throughout. Therefore, we can write that our m square v prime square is equal to our m square. First v square is as it is. Second, this will be our sine square plus cos square phi, which is equal to 1. This will be giving us v prime square minus, and m square we have taken as common, so this comes as 2 v prime cos of phi. Okay. And now we are going to use our energy equation, that is equation number 3, and multiply that equation by small m. Okay, and then sort it out. So you can say equation 3 multiply by small m. So from there we are going to get this as m capital M v square is equal to m small m, and that is our v prime square plus m square v prime square. And from here we can find out this m square v prime square. So we get this as our m square v prime square will be equal to, this will be a common, so this we get m small m, and we have v square minus, one second, this is, yeah, minus v prime square. So we are going to substitute it, and so we get from here m small m v square minus v prime square is equal to m square v square plus v prime square minus twice v prime and cos of phi. And here this m goes with this square, and we just open the brackets. We get this as our m v square minus m v prime square is equal to m v square plus m v prime square minus twice m v prime cos of phi. And now we can make it a quadratic in terms of our v prime square. Okay. And so we have here v prime here as well as v prime here. Therefore we can write this, we are going to get as v prime square m plus small m minus, and this term we are going to get this as our twice m v cos of phi times v prime, and then we are left with these two terms. We get plus v square, and we have m minus small m is equal to 0. So this is nothing but quadratic in v prime. Okay. And obviously we are interested in finding out, or we can say this quadratic equation is going to have a solution, or the solution of the quadratic equation is going to exist only if the discriminator is not negative. So from here we can say the equation, we can say the solution of this equation exists if our discriminator is greater than or equal to 0, which basically means b square minus 4ac should be greater than or equal to 0. B square minus 4ac should be greater than or equal to 0. Now we substitute this b square, and b square is our twice m v cos of phi whole square minus 4ac. A is our m plus m and c is our m minus m. V square is equal to 0. And we can just open the bracket and we are going to get this as our 4m square v square cos square phi. It should be greater than or equal to 0. Cos square phi minus 4, and this is our m square v square minus small m v square greater than or equal to 0. And our 4 cancels out throughout, and v square, we can just take it out, and then we can make m square as common. So we can say that our m square is equal to cos square phi minus 1 plus small m square is greater than or equal to 0. And from here we can write that our m square is greater than or equal to and we can say this is our m square 1 minus cos square phi, and we can write this as our m square sin square phi. So this gives us that our sin of phi is less than or equal to m upon capital M. Or for maximum value, we can write that sin of phi maximum will be equal to m upon capital M. Okay, so for this value of maximum angle, okay, that was our required solution. Come to the next question. This states that collection of identical point-like balls is arranged at equal angular separation along a semicircle arc of smooth horizontal frictionless table as in figure. The total mass of this ball is m, capital M. A single ball of mass m approaches the semicircle from the left with appropriately chosen initial conditions such that it undergoes a sequence of perfectly elastic collision with all n balls on the arc and finally exit the system moving directly backward to the left. Each ball in the semicircle has a mass m upon n. So based on this, we are having two questions. In the limit n tends to infinity, so that the mass of each individual ball m upon n is approximately 0, determine the minimum value of the ratio for which incoming ball can emerge traveling directly to the left. Part B, for the minimum value of m upon n obtained in part A, show that the ratio of the ball's final speed to the initial speed is e raised to power minus pi. So we have to solve these two questions, and the figure we can draw that we have balls which are arranged in a semicircle arc. Okay. So these are the balls which are arranged in the semicircle arc, something like this, and we have and the total mass of all these balls are m, and number of balls are our n, and we are given that we are having a ball of small mass m which is moving initially in this direction, and after collision with all these balls, it is coming out from exactly the opposite end. Okay, so this is the basic question diagram as per the question. Okay. And we are given that the total mass of the ball is m and number of balls are n. Therefore, based on this, we can write that mass of each ball, mass of each stationary ball let us suppose is given as mu, that mu will be equal to total mass of the balls and number of the balls. Okay. And we have to remember that this ball, small m, is going to strike one by one all these balls, okay, and then come out from the top side, and all these collisions are elastic collisions. Okay. So we have to find out the minimum value of this m upon m. That is our part A. And so from the figure we can you can say that initially the this ball of mass m is moving toward the right, and finally it is coming as our left. It means the total change in direction between the incoming and outgoing ball is our pi. Okay, this we can just make a, you can say, conclusion from the figure. So we can say that our total change in the direction of the ball, and let us call this ball as B. Okay, ball B, and suppose that is our delta theta. Therefore we can say that our delta theta is equal to our pi, because it is incoming from the going towards the right side and returning back to the left side. Okay. So if the total deflection is our n is pi, and the number of balls are our n, so from here we can find out that deflection per collision. So we can say that our deflection per collision, let us call this with theta, and this theta will be equal to total deflection divided by number of balls. So this is our deflection per collision. And we are going to make analysis of one collision, and then we can explorate to the other collisions. So we say one elastic collision, and for that we know that our incoming mass is our m, and let us suppose its velocity is our v, and the stationary mass is, we have calculated, is our mu, and therefore we are going to make analysis with respect to the center of mass. Okay, so we can say that center of mass velocity So for that, we are going to start with our momentum. So you can say total momentum before collision and before collision only the ball, only the mass m is moving. Okay, so that will be equal to P, and that is equal to m times v. and the total mass of the system. So we can say that our total mass is equal to m plus mu. That is the mass of our one elastic collision. So total mass is equal to m plus mu. So from here we can write that center of mass velocity is equal to our VCM. Then the VCM will be equal to our momentum is our mv and divided by total mass of both particles. One particle is having a mass of m, and that is the incoming mass, and we have stationary mass, which mass is mu. Okay. And now from here we are going to calculate the velocity in the center of mass frame before collision. So we are going to find out velocities of center of mass frame, and this is our before collision. And so first of all we are going to write velocity of mass small m in center of mass frame, and let us call this as um, and this um will be equal to its own velocity minus the center of mass velocity. So we can say that our um will be equal to v minus mv divided by m plus mu. And if we take a LCM, we can really see that this m, v and this is going to cancel out. So we are going to get this as m plus mu and mu times v. And we were having two objects. One was having mass m and other is having mass mu. So we can find out now velocity of mass mu in center of mass frame. Velocity of mass mu in center of mass frame, and let us call this as our u mu. Therefore we can write that our u mu is equal to our minus, because initially it was stationary, so that will be 0 minus, so directly we can write this as our m times v and m plus mu, because initially this mass mu was stationary. Okay. And now we are going to find out velocity in the center of mass after collision. And so we found out velocity of center of mass before collision. Okay, so next we are going to find out what is going to happen when the collision is going to take place, how the velocities are going to change. And for that we can call this as our center of mass frame scattering, because after the collision both masses are going to scatter. Okay, one is going to move towards, with respect to x-axis it will be moving on the positive side and the other one in the negative side. Okay. And so we know that in the center of mass frame we can write that speeds are unchanged in the elastic collision, only the direction can change. Okay. So you can say speeds are unchanged in elastic collision and only directions can change. And let us assume that theta is the angle between the final center of mass velocity of mass small m with respect to the original direction. So we can say that angle between center of mass velocity of mass small m and original direction is, let us suppose, our theta. Original direction was in terms of our x direction, and therefore we can write that our velocity of mass m, with this is the center of mass velocity but now after collision, and this we can write mu times v and m plus mu, okay, because the direction is going to change. Okay, so we are interested in the magnitude part only. And now we are going to reconvert this into velocity into lab frame. Okay. So we can say transform back to lab frame. Therefore, we can write that final velocity of mass small m in lab frame, and let us suppose that is given as v of m, then v of m will be equal to over um after collision plus velocity of our center of mass. Okay. And from here we can find out its component, x component as well as our y component. Okay. Therefore we can say that its x component will be equal to our mu times v and m plus mu cos of theta and plus velocity of the center of mass, that is at mv and m plus mu. And similarly we can write its y component, and that will be equal to over mv, and this is our m plus mu sine, sorry, this is theta not phi, theta, and this is also theta. And we are supposed to find out the maximum possible deflection. So you can say that maximum possible deflection in one collision and let us suppose that deflection angle is phi. You can say for deflection angle phi, we know that its tangent of phi should be our ratio of our y component and our x component. Okay. And we also know that our one second. And we also know that our maximum deflection occurs when the outgoing velocity vector is tangent to the velocity circle. Or simplest term we can write that our u of m after collision should be perpendicular to our velocity of center of mass, which basically means that the value of theta is equal to pi by 2. Okay, and this is for maximum deflection. Maximum deflection. Okay. And we are going to put theta equal to pi by 2 in x component as well as our y component. Therefore, we can write that v of x as theta is equal to pi by 2. This gives us a mv and m plus mu, and we have our y component theta is equal to pi by 2, which gives us mu v and m plus mu. And the magnitude, so we can say that our v will be equal to x component and y component. So this will be giving us v m plus mu, we can take as common, and inside we are left with this as our m square and mu square and its square root. So it means that our maximum, that is our sine phi maximum, will be equal to our y component and it's their net magnitude. So this gives us mu upon m square, mu square and its square root. And we are given that as number of balls tend to infinity, we can say that our mu is very much less than our small m. So from here we can say that sine of this maximum will be approximately equal to mu upon small m. So this is a maximum angle for one single collision. Okay. So you can say that this is the maximum possible deflection in a single collision. And we know that the total is our per deflection angle, we already know is our pi upon n. So that we are going to use because it is going to take n number of collisions. So it is only our, this entire discussion was based only for n collisions, single collisions. Okay. Now we are going to write with respect to the angle, we can say that the required deflection that is our theta is equal to our pi upon n, which we have already derived, and this should be always less than our maximum value of our deflection. Okay. And if his theta is very small, so we can write that our sine of theta is approximately equal to theta. Therefore we can say that pi upon n is less than equal to mu upon m. Okay. And mu we know is our m upon n. Therefore we get that our pi upon n is less than equal to, this comes as m and n m. And this n and n goes away. Therefore from here we can say that our pi is less than equal to m upon small m, and we are supposed to find out the minimum. Therefore we can say that m upon small m, its minimum is equal to pi. That is our part 1. And in part 2 we are going to find out the final speed ratio. Part B, and we already derived it, that speed after one collision, you already found out the speed after one collision, that so v is equal to v upon m plus mu and square root of m square plus mu square. But we also know that our mu is very much less than small m. Therefore we can say that square root of mu square m square can be approximately written as our m. Therefore we get that the velocity v is approximately equal to mv divided by m plus mu, and which we can write as a v 1 minus mu upon m. This we can easily write by using the binomial expansion. Okay, higher order terms we can neglect it. And this is speed after one collision, but we have n number of collisions. Okay. Therefore we can say that for n collisions, this for n collision we already solved, I think yesterday or day before yesterday, we solved a question that was for our n number of collisions. Okay, and we proved that for n number of collision the final velocity is equal to our initial velocity and 1 minus the ratio of their masses and raised to power n. Okay, this we proved already. So same we are going to replicate here also, and we can write that our v final oblique v initial will be equal to 1 minus mu upon m whole raised to power n. And we are going to use the condition for our, for that we know we are going to solve this particular part, and this is mu upon m, and mu is our m upon n, so this comes as m upon n times small m, and that is equal to nothing but our pi upon n. Therefore we get that 1 minus pi upon n whole raised to power n. So this entire term is reduced or modified into this term, and now we are going to take the limit n tends to infinity. You can say that our limit n tends to infinity, and we get this as, first of all let's write the general formula, 1 minus alpha n whole raised to power n, and that is equal to our e raised to power minus alpha, and here alpha is nothing but our pi. Therefore we get this is equal to e raised to power minus pi, and this is ratio of their final velocity to our initial velocity. That was our part B. Now we come to the next question. This question, it states that a particle of mass capital M moves with the initial velocity along a positive x-axis and undergoes a perfect elastic collision with a second particle of mass small m that is initially at rest. The collision is not necessarily head-on, so that after the collision, both particles may move off at angles. Let theta denote the angle that the velocity of particle m makes with the x-axis after the collision. Determine the value of theta for which the particle m attains the maximum possible speed in y direction. So this is basically same as elastic collision between two bodies. One body is at rest, other one is moving, and we are going to find out that a body whose mass is small m making angle of theta with the horizontal, okay, and it should be having a maximum possible speed, and that speed should be along y direction, and for that maximum possible speed we are going to find out for what value of theta that is going to happen. So this is quite simple, same to our first question, but here we are interested in finding out this maximum possible speed. In the first question we dealt with our maximum possible angle. So this is a major difference between the two. Basic method is going to remain same. So let us say that we have two masses. One mass is our capital M, and let us suppose its initial velocity is our vi, and that is suppose given as v0, and it is moving in x direction. Okay, so this is our initial velocity, and we are having a mass small m, and it is our rest, so its initial velocity is equal to 0. Okay, so it is initially at rest. And after collision, let us assume that our mass capital M is having a velocity of v of f, and mass small m is having a small v of f. Okay. And we are only interested in this small m, so we are going to resolve its velocity into two components. So this is our horizontal position, and let us suppose this m moves in this direction with the velocity vf at angle of theta. So we are going to get this as our vf cos of theta, and we are going to get this as our vf sine of theta. Therefore we can say for small mass m, for mass small m, we can write its final velocity, that is v of f, will be equal to our vf cos of theta I unit vector plus v of f sine theta j unit vector. And now we are going to use conservation of momentum. So you can say momentum conservation which basically means initial momentum is equal to our final momentum, and initially only mass capital M was moving, so we can write this as our m v of I plus m v of I is equal to m vf plus small m and small vf, and initially this vi was 0, and so we get from here, and this v initial is equal to v0, so we can write this as our m v0 I unit vector is equal to our m vf plus m small vf, and let us call this equation number 1. And now we are going to use our kinetic energy conservation, or simply we can write it as energy conservation, which means initial kinetic energy is our final kinetic energy, and we can write this over half m v naught square is equal to half m final velocity and half m final velocity, and this half cancels out throughout, and we can write this as our so let us modify this equation, and we can write this as our m vf square is equal to m v naught square minus m vf square. Let us call this equation number 2. And from equation number 1 we are going to find out what will be our vf. So you can say from equation 1 we can write our vf is equal to m v naught I unit vector minus m v of f divided by m, which can be further written as, we can say arrange this denominator, which will be giving us v naught I unit vector minus m upon capital M, and this comes as our vf. And now we can write that our vf square can be written as vf dot vf, which can be written as our v naught I minus m upon capital M vf dot v naught I minus m upon capital M and vf. And now it's a simple calculation. We get this as our v naught square minus, this will be coming as twice m upon capital M v naught vf cos of theta plus m square upon capital M square, and we have this as vf square. And we can now rearrange it. 1 second, let me, this is vf square, and we have our equation number 1 and 2. So we can write this as, we have a v naught square here and we have here vf. So let's rearrange it, and here's here. Therefore we can say that our n times v naught square minus, and this comes as our twice m upon capital M v naught vf cos of theta plus m square upon capital M square, and this is our vf square, and this will be equal to our m v naught square minus m vf square. And if we solve it, because this is a simple equation to solve, so from here we can get that our final velocity will be equal to twice m v naught cos of theta and m plus small m. And we are interested in finding out the, or maximizing the y component of the velocity. Therefore we can say that y component of velocity maximized. So we can write its y component. So we have our v of y, we know is our v of y sine theta, and v of y already calculated. So this comes as twice m v naught cos of theta m plus small mn sine of theta, and we can just combine these two, cos theta and sine theta, giving us sine 2 theta. So this gives us m v naught m plus small m and sine of 2 theta, and we want that this vertical component should be maximum. So it means that our Vy should be equal to our Vy maximum, and this is only possible if this sine of 2 theta is equal to 1. Okay. Therefore, we can write value of theta is equal to our pi by 4. So for this value of theta, we are going to get the maximum value of our vertical component of the velocity after the collision. Okay. So these were the 3 questions that were based on the collision, elastic collision, in which we majorly did conservation of energy as well as conservation of momentum. Okay. And so this completes all the 3 questions. Thank you.